there's a lot of work to do, but we want to build this. So I've already built it. I'm going to show you this. This is a wave pulse on a string. I'm going to run it, and then we're going to go through all the steps to build this in Python. It's going to be long and complicated. So here's a wave pulse on a string. It hits to the end. It flips upside down. That's what should happen. It really works pretty well, and I'm pretty surprised that it works at all. And there you go. We're going to build this in Web VPython. So we need to start with some stuff about waves. So let's jump over to the paper and talk about waves. Waves on a string. Okay. So here's my wave pulse I want to model. We have this is the wave equation. The wave equation is a relationship between both space and time, right? So the displacement and changes with both time and space with this wave equation. And t is the tension in the string, mu is the linear density, and the velocity of the wave would be the square root of that. So the thing is that we want to do this in Python, we need to break this into steps. We're going to break this into both steps of time and space. But let's deal with just space first. So how do I deal with this derivative in space? Well, imagine that I break the string into finite segments, finite element pieces, and each one is separated by the same spacing delta x. Okay, so they're just data values, they're values. And I can label them yi, that's the next one would be yi plus 1, yi minus 1 would be the one before it. So they're all indexed by this I. Well, we can write the definition for the derivative. Let's write the derivative at the half point right here. I'm going to write the derivative at the half point right here. Well, it's going to be the final position minus the initial position divided by delta x. So I can write that as y, I'll write it as y prime. That's the derivative. Y prime at I minus 1/2, right, because it's a halfway point, that's where it's going to be, is equal to yi minus yi minus 1 over delta x. That's just the slope. Now, if I want to find the second derivative, y double prime at I, it's going to be the change in slope from half to half, right? So we can write this as yi plus a half prime minus yi minus a half prime over delta x. And then these, I can use this up here. So with that, I get the following. yi double prime is going to be this derivative right here, which is, there's a delta x over delta x. I'm going to get delta x squared on the bottom. But up here I have yi plus 1 minus yi minus the slope here, which is yi minus this, which is going to be, so it's going to be plus yi minus 1, right? Because it's minus a negative. And all of that's over delta x squared. So if we just combine terms, I have this is going to be equal to yi plus 1 plus yi minus 1 minus 2 yi over delta x squared. So that's my derivative. Now, what about time? So let's go over here and draw our points again. I'm going to draw fewer just so that we can deal with it. And then if I had another color, here's a color. This might be too big. So I could have, this is yi. I could also have another y value there for the future. I could also have one for the past, which I should do another color. Okay, so all these will have different values. They'll change in time. So let's call this, in the future, yi k plus 1. So I'm going to give it two indices. I have discrete values in time at discrete locations in space. So yik plus 1, this is going to be yik, and this will be yik minus 1. So the two indices, one changes in space, one changes in time, which we're going to draw as an animation. So with that, I could say the derivative, the second derivative of y with respect to time is going to be the same thing, right? We're just going to, except we're going to be changing the k index. So I can do the same thing, find the derivative and the second derivative. I'd get the same thing. Y, and I'm going to include the I here too. yi k plus 1 plus yi k minus 1 minus 2yi k over delta t squared. Right? And that looks just like the other one, except it's got k plus 1, k minus 1, and k. They're all i's. Well, now that we have an expression for the second derivative of time, we have an expression for the second derivative in space, although it's wrong. I need to go back over here and put k, 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 right? Because they have two indices now. I can set those two into the wave equation, and let's just call this value right here. I'm going to call that just r. No, wait, I'm going to not yet. Let's hold on to that. I'm going to call something else r. So let's just put in our expression for everything here. So I have the second derivative with time is this. I'll write it out. Y I k plus 1 plus y I k minus 1 minus 2 y I k over delta t squared equals t over mu y I plus 1k plus y I minus 1k minus 2 ik. Yeah, all over delta x squared. So these are really partial derivatives because I didn't change the k. See, the k is my time. Time didn't change. Here, space didn't change. But let's just think about this. So we can go through all these elements, and I know I can find the one before it and the one after it, except for the first and the last one, which is an issue. Those are my boundary conditions, right? Those are fixed, and we'll deal with that in a second. So I can go through and find all my y values. And what I want to do is to find out where it's going to be in the next time. So where is it going to be in the next time? If I look over here, that is this. Y I k plus 1. That's the future position of the element I. So I want to solve this for y. I want to solve this whole thing for y I k plus 1. So I'm going to multiply both sides by delta t, and then I get, let's just write it out, y I k plus 1 plus y I k minus 1 minus 2 y I k equals t delta t squared over mu delta x squared times y I plus 1k y plus y I minus 1k minus 2ik. And then I can just add that to both sides, subtract that, and I get my solution. Y I k plus 1 equals 2 y I k minus y I k minus 1 plus, now this is where I'm going to call this r, just because I don't want to write that, y I plus 1k plus y I minus 1k minus 2y. That was weird. Y-I-K. Okay. So let's just think about this in terms of our changing values, right? Because I have space and time. And so all of these are either a space or time. So this is this element now, because it's K. This is this element in the past, the previous one. Okay, I'm going to call that old. Call that now. I'm going to call this old. And then this is now, because it's k, but it's this element, it's k plus 1, so it's that one right there. This one is now, because it's k, but it's that one over there. And then this one is this one now. So if I know all those things and the previous versions, I can find the next version. Does that make sense? So we can do this in Python, right? So we're going to do this in Python. Here's what we're going to do. We are going to do a bunch of stuff, and if you've solved a finite difference problem, that's fine. So here's our stuff. There's my endpoints. I'm going to make 3 lists. I'm going to make 3 lists called y old, and it's going to be a list of all the data values at the different x values in the past time. Y now is a list, and then y new is a list, right? So those are my k minus 1, k plus 1. and then the space-wise, they're just going to be spaced out. Okay. And then what I'm going to do is to go through my list. If I know now and old, I can use this equation to find my y new. And then once I do that, then I'm just going to make my old equal to my now and my now equal to my new, and then do it again. Right? So I need to know where they were before. I can find out the new values and move on with my life, and it's going to be great. Okay. I'm going to assume you've done something with Python lists before. If you haven't, it's going to be a little rough, but you can hang on for a wild ride. It's going to be great. Let's just do it. Okay. I'm not using that one. I'm using this one right here. See, is that right? Yep. Okay, so I've already put in some stuff, obviously. I have my dx, my dt, the length of the wire, my tension, my linear density. This is the mass per meter. Let's make we're obviously going to make a graph. G1 equals graph. X title needs to be bigger. Bigger. That's better. I like it. I like it big. Just easier to see. X title equals X. Y title equals Y. Width equals 400. Height equals 200. So just a reminder here. We're plotting a picture of the string, and to how we're going to show it with time too. Well, we're going to animate the graph. So we're going to make an animated graph because we're going to move time forward and change the new value of the graph. Okay. So this is the graph we're going to plot. G curve color equals color.blue. Okay, I got all that. So now the first thing I need to do is to I have my dx value. I need to make my x's. Right? I need to make all my x's. So let's do that down here. I'm going to say xt equals 0. That's my temporary x value. And then x is just my list of x values. While xt is less than or equal to L, because I'm going to increase the value of dx, I need to add my x value to my list. So x equals x plus xt. And then I need to increase my value of xt. Xt equals xt plus dx, and let's just print that to see if it's doing what we want. We never know. Print, and which is going to be 100 unit long, but that's fine. Let's just make sure it's running. Okay, so there you see that I only go up to 0.99. I don't have that last value, so I need to get that last value in there. I can do that by just down here. I'm just going to do it the simple way. X equals x plus xt. So I'm going to add one more xt value, right? Because it got increased right there, and then it stopped the list. So if I do this, it should have that last 100, that 1.00 value in there right there. So that's good. Okay, now I need to make 3 lists. I need to make a y old. I need to make a y now. I need to make a y new. So let's make those. I'm going to start with something useful, but y old is an empty list. Y now is an empty list. Y new is an empty list. And I need to go through and add stuff in there. So I want to make sure it's the same size as my x. So I'm going to use x to go through this. For I in range length of x. So this will go through all the x values and label them and call it I, the index I, and then we can use that. So I'm just going to put a sign function in my graph to begin with, just because I think it's cool. So y old equals y old plus, let's say 0.1, that's the amplitude, I'm just picking a value, doesn't really matter, times the sine of pi times xi divided by L. Yep. And I'm going to make that the same thing for new and now. So let's just change this to now. So they're all going to be the same, and that's fine. I don't even need to do new because I'm going to make it, but later, but this is fine. I need to have some values there. Now, I think we're ready. I feel like I'm missing something. I need t. I got dt already. So let's just go through our list and change these values based on that equation that we had, right? While t is less than 5. Now I'm going to make an animated graph. So to make an animated graph, number one, I need to give it a rate. So let's do a rate of, let's say, what's dt? 0.05. Let's say 50. Let's just see. I don't know. Maybe it's too slow, too fast. And then I need to, in order to make an animated graph, I need to reset my data for my graph. So I'm going to make a list called F1 data, and it needs to be empty. And then I'm going to add my data points there to graph it. If you can't remember how to make an animated graph, I forget all the time too. It's not a big deal. Okay, for I in range 1 length of x minus 1. So I'm going to go through the list and use those values of old and now to find the new values. But I can't change the first element in the list. I can't change the last element. Those are fixed points. And also I don't have a data point before it to calculate stuff. So that's a problem. But this list, this loop only starts at the second element and ends at the second to last element. So that's good. We won't have that problem. Now I'm going to type my equation. Y new I, right? I'm looking at my equation, equals 2 times y now I. Whenever I see k, that's now. K plus 1, new. K minus 1, old. Y now I minus y old I plus r times, that's that constant, y now I plus 1 plus y now I minus 1. Can't see it because of my big old face. There. Minus 2 times y now I. And that's it. So I've updated them all. Yay me. Yay us. Okay. So, but now what I need to do is go through my list again. And I need to update my old values, right? And I make my now values. I don't want to do now first because then when I go to do the old, it'll mess it up. So for I in range length of x, y old I equals y now I. So it's going to update all my old values. And you can't just say y old equals y now. You can make two lists equal, but they will always be equal. And when one changes, the other one changes. This one will change the elements and keep them separate, though. Now I can do the now for I in range length of x. Y now I equals y new I. And now I want to make a graph. So I'm going to go through the list again. Let's plot the new. For I in range length of x, f1 data equals f1 data plus x, xi. That's what I'm going to plot on the horizontal. And then y new I. Now I can graph it. F1.data equals F1 data. And then I need to update my value of time. T equals T plus dt. If this works, I'm going to be really surprised because there's a lot of places I could have made an error. I'm just giving you preemptive excuse. If it crashes, I should save it. And let's run it. Hopefully it works. Okay, it didn't work. So something happened. Something bad. Now we got to figure out what. Let's just plot this right here. I think that might be something weird. For I in range length of x, f1 dot plot xi y now I. And then let's stop it. So put t equals 5, so it won't run. T equals 6. All that stuff won't run. Okay, that's good. Okay, see, that's how you troubleshoot. Now, what am I doing wrong here? So 0. Let's put this at 10. Let's make it run slower. See if we can see what's happening. It goes back and forth and then blows up. T over mu dt squared dx squared. let's see, dt squared over x squared t over mu, a t over mu. Oh, I did this wrong. I got this backwards. So I had an unrealistic situation before. I had t over mu was 0.04. So let's put this at 400 divided by 0.1. 0.01. Yeah. No, it did it again. Let's see. So t over, let's put this at, I know that I had this at 0.04 worked. Let's put that right there. Yeah, there it goes. So I just picked a bad value. It is sensitive to your conditions are sensitive. Now, let's make this look a little bit better because it's zooming in and out. Let's just fix that. I'm going to put my amplitude of my graph is 0.1. So let's put y max equals 0.15, y min equals negative 0.15, and then I can increase this rate a little bit. Let's put it back at 50, and let's run this. Okay, so that's a standing wave, right? And that is a solution to this. And the time's all weird and stuff like that. It's taking 5 seconds. I know that. Okay, but you know, if it was really going too fast, it just wouldn't look great. So the math is all that really matters. And it only went through one oscillation, and that's fine. Let's just, for fun, let's put in a full sine wave so you can see it oscillate like that. I can do that pretty easily down here. I'm just going to put, say, 2 pi. 2 pi. 2 pi. There you go. So we did it. We did it. Okay. Now I want to put a little wave pulse. So let's do the following. Let's put all these at 0. I'm just going to multiply by 0. Just in case I want to go back and do it the old way, I can just take out those zeros. That's just a nice way to do it. Of course, if I run it now, I have a string that's no displacement. It's not going to do anything. That's boring. So what we want to do is, I don't even need to plot this. This wasn't needed. I want to go through and I'm going to have a little sine wave hump, right? And so I'm going to have a width of that sine wave. Let's call that the width of that 0.1. And the amplitude of that 0.1, just because that's what we had before, and the initial x value, right? Where does it start? So let's say x0 is at the initial of that hump. Let's say it's at 0.2. I'm just picking things. So if I do that, I can go back through my list. So for I in range length of x. Now, if my x, they're all zeros, right? But if my x value is greater than x0, then I'm going to change it with this equation. So I can put in here, if xi is greater than or equal to x0, then I'm going to greater than or equal to x0. Then I'm going to change that element for both the old and the now. The new doesn't matter, because I'm gonna calculate that anyway. So y old I equals a times sine of pi times xi minus xo, right? Because I want to start, that's like my new origin, and divide by the width of my whole pulse, which is going to be w. It's not L. And then I'm going to do the same thing for y now. Let's see what happens. I think it should work. Should I save it? Yeah, I should save it. That didn't look right. It looks cool. Oh, I see. If xi is less than that and xi is less than or equal to xo plus w, right? Because I don't want to, I'm changing all the other ones later too. I don't want to do that. There we go. There's my wave pulse. So you'll notice that's not what the same thing I had. What happened was I started with the string like this, and then it just went down and collapsed, and it made 2 pulses, while although cool is not what we wanted. Okay. So what we need to do, let's go back to the paper for a second. Remember, I set my y, I had my 2 initial functions, y old and y now, and I had them the same thing. How do I make a pulse start off like this with some velocity v? Well, I have the pulse right there, and that's my now. But what I need to do is to make an old, a y old, like this. So I need to give 2 different values for y now and y old. And so this pulse is at 1 time before it. So I can find out the location of that. I'll say x new, let's say it's called x old 0. That's a dumb name. X olodo is going to be equal to how far is that shifted, right? How far is it shifted? Well, it's v times delta t. The velocity of the wave times the time shift. And then I can find that distance. So that's going to be my new x. It's actually going to be this. It's going to be xo minus v delta t. And let's just call that x negative 1. I'm going to call it that. All right, so I'm going to shift it over. So it does depend on my time step, but that's going to make sure my wave's moving with that velocity because that whole pulse moved that distance in that amount of time. That's not too hard, right? So that just means I'm going to have a different value for y now and y old. I've already got y now. I just make a different y old. So down here, I need the velocity. Did I put that in here? So there's that's my t over mu right there. So v is going to be the square root of 0.04. I made a mistake somewhere. I don't want to fix it. Divide. Oh yeah, that needs to be, well, whatever. It doesn't really matter. That's going to be fine. We fix that later. Fix it. We'll do it live. Don't worry. So down here is where I change x now. So I'm going to comment out the old, and I'm going to copy all of this. And I'm going to change the old and not the now. And in this case, I need to calculate that xn1. It's going to be equal to xo minus v times dt. Just like I said. There's no magic there. And then over here, I'm going to say if it's less than x new 1 and x new 1, just change these to new ones. That's it. That should do it. So now we have the old and the new are different. Before we had them the same, which meant it started with an initial velocity of 0. Now it's not doing that. I'm scared to run this, but if it does, I win. I'm pretty excited. It worked pretty well. And that's pretty much the same thing we got before. Okay, so now if you want some homework, what would be kind of fun, try different shapes. You could really put any shape you want in here. Try not to have like a complete square shape, because then you're going from the 2 values. It's not actually square because it depends on the width. It should still work. You can make a square wave. You can make any kind of pulse. It's fun. And then you could do things like this. Have 2 pulses starting off. 2. And they're coming towards each other like this, and see what happens when they overlap. And then, or what if they're upside down? So you can make all sorts of things like that. You'd have to put those in the function though. So, but that's that. Okay, so I'm going to give you the link to this code. Saving it right now. Link will be down below. And that's that. Hope you had fun. I had fun. It was great. Great time. Talk to you later.